Hello everyone, my name is Abhishek Bansal. In this video, I am going to design a flyback converter. So in my video flyback, you would have learned that what is basically a flyback topology is. In this video, I am going to design a flyback converter using a flyback transformer and a flyback topology. So basically what I am going, this is my design example 1. Design example 1. So in this we are going to take the input 18 volts to 36 volts, and the output required is it would be a dual output circuit. Dual output. The first one output is basically a 5 volt 4 amperes, and the second output is a 10 volt 20 milliamperes. Excuse me. Yeah. So we know that flyback topology is going to be like this way. We are having here a DC input only. So this is a flyback topology, and I am going to have a flyback transformer here. I am going to draw a flyback transformer, and here this is also flyback transformer. Actually, what do I take the whole board? So this is the input, and this is a flyback transformer here. This is the dot end of the winding, and here the dot end of the winding is here. Okay, this is a half wave rectifier, and this is an output capacitor. This is a diode. Okay, so this is, now we are going to have an output here. Okay, and we have seen we are having a switch, which is basically I am going to use a MOSFET here. Okay, so this is the circuit that I have done the analysis when I have made the video of flyback. Okay, so now I am going to design the flyback converter. To drive this, I am going to use some IC. The vendor name of the IC I am not taking, because any of the vendors which are available in the market, any of the semiconductor leaders, whether it's an Infineon, NXP, Texas Instruments, Microchip, or the others, whatever, you can use any of the. This would be driven by an IC here. Okay, and this would be, I am going to have a bias winding here, bias here, not winding here, bias here, and I am going to have a UV yellow. This is basically the chip has the pins, which is one name is gate. This is a bias. This is an UV yellow. This is an AGND, and this is a P good and this is an RT pin, SS pin, comp pin, FB pin, PGND, CS pin, and PGND. Okay, I am going to go into the detail of what these pins are. So this and there would be an optocoupler here. We have an optocoupler here. So an optocoupler here is this. Okay, this would be a resistor here, and this is definitely going to have a we have a capacitor here, resistance here, we have again a resistor here. Okay, this is again a grounding here, and it would be here line connected here. Excuse me. This is again a here I am going to take a input here, and is a input capacitor here. I am just putting the ground here. From this input line I am going to have a this would be connected to a UVLO, or that's the sink. This is going to be connected to an AGND. The bias pin will go to this again the input line, and we are having the VCC here supply, which we are going to take from an auxiliary here. We have a capacitor here, and it's again a grounded here, and so this we are going to connect it like this way. This is basically okay. This is included. The gate pin would be dragged to this MOSFET. The CS pin would be connected to the source pin. This CS pin, source pin. Okay. Here we are going to have a resistor. From the resistor pin we are going to have a PGND. This phase FV pin is going to be a grounded pin, and so I have drawn an optocoupler here. Up to this comp pin is going to be to the this is going to be this same pin Vox, and we are going to have some resistor here. Okay, this will be here, and here we are going to have an again C and then resistor and a capacitor and a resistor, which is again the grounded here, and this would be here. So this is the complete circuit diagram which is going to work, and this is the small PCBs which you have seen, like many bloggers have even posted, and this is what you are going to find on the net, and this is a complete circuit which is going to make us achieve what we need. So basically I have taken here a particular IC, and this IC is basically this particular IC. It can be of any vendor. It can be like even this IC has a limitation on the input, and then what would be the input operating range, what could the maximum output it could provide, what is the and if suppose if this has a specialty. Let's suppose I am taking it for a clarification, like if suppose I am going to take an input, is basically we know the input into here would be 18 to 36 volt. So the operating voltage that this IC need is basically a 2.9 volts to the 45 volts, and if this pin has a specialty, I said that if suppose the bias is greater than or equal to 2.9 volts, that is the minimum operating range here. So this is the minimum boost supply of 1.5 volt. The input transient protection of this is given to by the 50 volts, and the minimized battery drain, like during the shutdown operation, it's less than 2.6 microamperes, and during an operating current it's basically less than 700 microampere. The switching frequency with this IC can hold is basically 2.2 megahertz. Even in my flyback quantity I have mentioned that the switching operating frequency for these kind of switching mode supplies goes to 2 megahertz. It's by the data sheet it's basically 2.2 megahertz. Okay, so it has an integrated error amplifier, so it's basically going to allow a primary side regulation without an optocoupler even, and minimize undershoot during the cranking. That means it during the start and the stop application. The other features of this IC is basically it has integrated internal uh, protection features of a constant current limiting over the input voltage. Okay, I will be going on the what basically inside the IC is after mentioning the because actually the board space is less, I cannot draw it everything here. So okay, let's go on. Let's see, because I have to do mention the calculations also, and I will be also mentioning the what this IC is actually all about. RAS circuit is what is basically known. These things I have added, so I have to explain every this thing here. So okay, let's see what are the pins here. I have said here a PG and D pin, that's a power ground pin. The source connection to the internal and channel power MOSFET. We have a VCC pin. It's a internal VCC regulator. Here the supply voltage input of the internal MOSFET driver. So we can connect a 5 ohm resistor in series with a 1 microfarad ceramic bypass capacitor from this pin to ground, and we have a bias pin here. That's the supply pin. The supply voltage input to the VCC regulator is achieved from this bias pin here. This is basically output. This is not an this is an output of the internal VCC regulator. This is the supply input voltage to the VCC regulator. So again we can connect a bypass capacitor from this pin to the PG&D pin. We are having a P good pin that I have not drawn here because I have not used it in the supply. That's a power good indicator. That's an open drain output that goes low if the FV pin is below the under voltage threshold. Okay, we can again connect a pull up resistor from the P good pin, which I haven't used in this circuit, and we have an RT pin. RT pin is the switching frequency setting pin, and as by the dataset we need a resistor between RT and ground. So this is basically we have done an RT and ground pin I have not drawn, so we need to put a resistor here to the ground. Okay, so this UC UVLO is basically an under voltage. UV means under voltage, U for under voltage, UV for under voltage, and LO is the lockout. So this is a UVLO pin, which is also known as sync or the enable pin. So this is the converter like a startup and a shutdown levels. It can be programmed using the pin to the supply voltage through a voltage divider. You can see I have used a voltage divider here. I have used a voltage divider. Okay, so basically this pin is going here. This is a voltage divider here. So if this pin is basically programmable, and if this pin is used, we have to connect the low side of the under voltage lockout resistor to the AG&D. So this pin we cannot left it open, and if we are not using this pin, like I have not used the PG&D pin here, power good pin, there's a power good indicator I have not used. If suppose I do not want to use this pin, when I do not want to use this pin, that means I do not want the converter. We are not setting up any the startup and the shutdown levels of this converter, and in that time the UVLO pin is going to be connected to the bias pin. We have to connect it, and AG&D means an analog ground pin here. Okay, one thing I forgot here is that this is also a external synchronization, clock input pin. So the internal clock, we can set the internal clock of this IC. We can be synchronized to an external clock by applying a negative pulse signal to the into the pin. So this is an analog ground AG&D. We can connect to the analog ground plane through the wide and the short path. We have a comp pin, that's basically the output of the internal transconductance error amplifier. So that's basically the comp is the loop compensation components. We are connected through this compensation pin on this. So between the pin and the ground, you have seen that I have connected here C and R, optocoupler, auxiliary. This I am going to come, and we have an FB pin here. So that is an inverting input of the error amplifier. Again, the FB pin I have set it to the ground here, but like we can connect this FB pin again to the we can connect this FB pin. I haven't used the FB pin, I have grounded it, but we can use this FB pin because that's an inverting input. It's an input pin. Okay, so it's an inverting input of the error amplifier. We can connect a voltage divider to set the output voltage. Like suppose if because this IC can be used for boost purposes, the septic topology, that's a single-ended primary, or this flyback. So when I am going to, we can connect the output voltage to this here, or we can connect the low side feedback resistor close to the AG&D. So next pin that I have mentioned, an SS pin here. SS pin here, again I have forgotten here to draw capacitor to the ground. The SS pin is basically the soft start. SS means soft start. It's a soft start time programming pin. So an external capacitor and an internal current source sets the ramp rate current of the internal error amplifier reference. So during the startup, okay. So we have to connect the ground pin, ground connection of the capacitor to the ground. We have a mode pin here. Just a second. Yeah, we have a mode pin also. So the mode pin, like the mode can be a 0 volt, 370 millivolts for this particular IC only, or 620 millivolt, or a greater than 1 volt. So when it's a 0 volt, or we can connect it to the AG&D during the initial power up. So an hiccup mode protection is disabled here, and the spectrum is disabled. If the mode is chosen, we want to choose the mode because we can choose the 4 kinds of modes are given here. So I can choose the mode 0 volt or by connecting it to the AG&D during, okay. And if I am going to connect 37.4 kilo ohm resistor, the mode I have not drawn here because I haven't used in this circuit diagram, but I am going to explain the particular features of this IC. So if this we are going to connect 37.4 kilo ohms resistor between this pin and the AG&D during the initial power up, the hiccup mode protection will get enabled, and also the spectrum will get enabled. If I have to use the third mode is the 620 millivolts, that means and to achieve it I need to connect the resistor value of 62 kilo ohms, and it would be again between this pin and the AG&D during the initial power up. Again in this mode the hiccup mode protection is going to be enabled along with the spectrum. If I want to use the mode greater than 1 volt, I need a resistor of 100 kilo ohms, and that's again going to connect it between this pin and the AG&D during the initial power up. And again, and here it's sorry, in the here the hiccup mode is disabled and the spectrum is enabled. So basically one we are getting a hiccup mode and one I am getting a spectrum. So that's why we are a spectrum. So that's why we are having a 4 modes. In one mode, when the mode is 0 volt, both are disabled. When the mode is 370 millivolts, both are enabled. I just said a wrong thing because, and in the third mode I said the wrong thing. when the mode is 620 millivolts, the hiccup mode is enabled, but the spread spectrum is not enabled, it's disabled. And if we want to use greater than 1 volt, we need to have a 100 kilo ohm resistor between this pin and the AGND, and the hiccup mode is going to be disabled, and the spread spectrum pin is going to be enabled. So now we have one more pin, that is SW pin, switch pin. So it's a drain current connection of the internal N channel power MOSFET, and lastly we have an EP pin. So that's I'm not going to again use it because that's an exposed pad of this package. So the exposed pad is going to be must be connected to the AGND, and the large ground copper plane to decrease the thermal resistance. Okay, so we have got here that this has a peak minimum peak current limit is what, 4.4. It depends upon an IC whether let's suppose say the peak current is basically 6.5 amperes, or even what is basically the maximum voltage that we can get if wanted to use for the boost operation, because here it's a 45 volt is the in operating range maximum. So but we can get only a 48 volts maximum here. So we are seeing is here that we are seeing here. Let me go here then. Yeah. We are basically seeing that the bias pin that it operates up to 45 volts. Then the absolute rating is 50 volts, and so basically this is basically used in an automotive supplies, and the minimum the switching frequency I have already said is 2.2 megahertz. The minimum switching frequency would be this IC can give, or it can be programmed dynamically from 100 kilohertz. So if we want to have if we are using a switching frequency of 2.2 megahertz, it minimizes the AM band interference. Okay, and if you want to use an EMI of the power supply, this device provides a dual random spread spectrum that reduces an EMI over the wide frequency range. So this features an accurate peak current over the input voltage, and which avoids the over designing of the power indicator, or the power or whatever to say inductor. So the low operating current and the pulse keeping operation, if you the higher efficiency at light loads is achieved by the features which this IC give, and those features are low operating current and the pulse keeping operation. This has internal features that have built-in protection features like an over voltage protection, line under voltage protection, thermal shutdown, selectable hiccup mode overload protection, and the features which is going to include is a low shutdown IQ and a programmable soft start, precision reference, power good indicator, and an external clock synchronization. So in the beginning I have mentioned that what is basically the input voltage is basically 2.9 volts. So what basically this device or this IC can do, basically we can use a single cell battery, or like okay, we can use a minimum volt, it needs a 2.9 volts. So I can power up this IC using a single cell battery, and it can even operate with a low voltage of 1.5 volts. That's what I have mentioned internally, that if the bias pin is greater than 2.9 volts, it can operate with internal voltage as low as 1.5 volts. So the internal, okay, so basically if we have to see the functional block diagram of this IC alone, that I because I do not want to erase the circuit, I will go the power the internal functional diagram after erasing this. But before, let me complete the what the circuit is basically. So in this design, we are going to design a non-synchronous. The design example is basically we're designing a non-synchronous low side and FET controller. Here, that's an isolated flyback regulator. So we are going to okay, let's come here to this thing. So we are basically the input is basically 18 to 36 volts for this circuit. Not I'm not talking of now the IC, because IC I want to explain with this block diagram, and that I will do after raising the board. So let's go to the completion of circuit, what are these components are and how the circuit is going to work. So the input, the circuit can work between 18 to 36 volt. The nominal the chosen is 24 volts, and I mentioned that we need two outputs. One was the 5 volt 4 amperes and another was the 10 volt 20 milliamperes. So it makes an output P out 20.2 watts, and here I am going to use the switching frequency 250 kilohertz. Okay, and this switching frequency we have used with the minimization of the switching losses and the conduction losses of the switching MOSFET. So let's go to the switching frequency. So I mentioned that in the pin description of this IC, that the switching frequency is basically set by this RT pin, and RT pin is the switching frequency setting pin. We need a resistor here, that I have put a resistor here. So we need to choose the value of this resistor. What would be the value of this resistor? Now we need a I am going to erase this side only. I don't know if this would be, I am removing this capacitor also here. So this should be no obvious, because now we are going to do an RT here. So for an RT here, we need, so basically we are setting the frequency of the internal oscillator of this IC, and it's basically 2.21 into 10 to the power 10 by switching frequency minus 955 equal to RT. So this is the formula to choose the value of an RT. This is the formula which is given by that vendor only, and the vendor says that we to choose the value for an RT. Like if suppose now whatever switching frequency we want to put, we can put 250 kilohertz here in this formula. Okay, and once we are going to solve, we are going to get some X kilo ohms. So that would be the standard value of the resistor. We are going to choose it. Okay, now we have a flyback transformer here, and we have to now select what is the mode of conduction mode we are basically choosing, continuous conduction mode or discontinuous conduction mode. Here I am going to use a CCM, the continuous conduction mode, so that I can minimize the primary side RMS currents and maximize the full load efficiency while minimizing the voltage ripple. Okay, so in the CCM operation, so here if you are going to see what is basically the duty cycle formula. So this is formula which is given by the data sheet only. You have to look into the data sheet for designing it. So the data sheet says that the duty cycle would be basically a NP by NS, that is the number of turns of primary or the number of turns secondary, V load voltage divided by V supply, this is here, remove it, this V supply plus again NP by NS into V load. So if using the putting the values in this, we are going to get the duty cycle. So the duty cycle occurs, so we can choose the maximum duty cycle here, and the maximum duty cycle can occur where the supply voltage is at the minimum value. Okay, and by choosing the maximum duty cycle, we are going to choose the number of turns of the secondary winding. And as I have said here, I am going to use a duty cycle of less than 50% because I want to have a buck operation from this flyback transformer. And that was basically the theoretical that if we are going to use a duty cycle less than 0.5 or duty cycle greater than 0.5. Now, but if we are going to because I am going to use this IC, and if I am going to so suppose the duty cycle gets increased to greater than 50%, in that I would be requiring a slow compensation, and this slow compensation would be set up here. We will, next thing we are going to see that the right half plane 0 of the modulator is pushed to high frequencies. So it's going to help to improve the low transient response. And here I have choose the maximum D max to be 0.4. Okay, if I say the maximum, I have just mentioned that we have to first select what would be the number of turns on the secondary side winding. So I have choose the duty cycle of 0.4. That's basically I am choosing a 40% duty max, that is the maximum duty cycle. So putting this for 0.4 here, and we know V load, what I have mentioned, the V load voltage is what, 5 volts. So it's a 5 volt there, and we can basically get the number of turns. We know what is the supply voltage. I have mentioned 18 to 36 volts. So 18 we are going to put here. Okay, 18 we are going to put here. And what now I do, because I need actually space, I want to write it, so I remove this IC because next circuit I think would be more easily can be easily explained now. Okay, so yeah, what basically I have said that D is equal to NP by NS V load divided by V supply plus NP by NS by into V load. Okay, so this was the formula that we have to use to calculate the number of turns. So let's rearrange it, taking it to that side or that side. We get NS what? V load 1 minus D max into NP divided by V supply D max. So I am going to take the minimum supply, that was 18 volt. V load we know it's a 5 volt. D max we know 0.4. We have selected ourselves only. NP I am assuming it here the 1. Again D's value is known. So we know the number of turns of the secondary. Okay. So we can basically we have selected n number of turns here, we have got it. So now we need a primary winding inductance selection now. So the three we need, basically we need, now we want to select it. I am just removing it. So we now basically want to get a primary winding inductance selection. So this is going to depend on three parameters. One is basically the primary winding, it's an ILRR. So it's a primary winding current ripple ratio, RR ripple ratio. Okay. The next thing, it's going to depend on falling slope of the transformer current, and the third is going to depend on the right half plane of zero frequency. That means it's an omega Z by ZR. I'm going to denote it by this thing. That's basically the right half plane zero frequency, okay, of the control loop. So if we need to have the balance in between these three things. Third thing is there. The falling slope I have not written here. Falling slope of the transformer current. So the primary winding ripple current ratio is selected to balance the copper loss and the core loss of the transformer, and as the relative ripple current increases, the core losses increases and the copper losses decreases, and the falling slope of the transformer current should be small enough to prevent the some harmonic oscillation. Okay, and this is basically much more needed when we are going to use the duty cycle greater than 0.5, because the IC I have mentioned that can even give us can even boost the supply. And if we are going to use a relatively larger inductance value of the primary winding, it is going to result in a smaller falling slope. Okay, and the right half plane 0, it should be placed at high frequency. It's allowing for a higher crossover frequency of the control loop. And again, as the relative inductance value of the primary winding decreases, it decreases the right half plane zero frequency. As our inductance value is going to decrease, the right half plane zero value is going to increase. Right half this frequency. So a maximum ripple ratio is going to be between a 30% to 70%, and it gives us a good balance of the total power loss of the transformer, matching the downslope of the transformer current to the internal slope compensation, and increasing the right half plane zero frequency. The maximum ripple ratio of the inductor is we are going to set to the 60%. Okay, as I said, we are going to use the CCM mode. In the CCM mode, the maximum primary winding ripple current occurs when the supply voltage is at the maximum value. So what is basically the primary inductance value we are going to now get? The formula that we are going to use. The formula that we are going to use is the number of primary turns square, the supply voltage square, again V load square by ILRR, that's basically the ripple ratio, or I just mentioned what is basically it's the primary winding ripple current ratio into switching frequency into P out into, is this I am writing here rather than there, into number of secondary turns into V supply again plus NP into V load the whole square. So using this formula we can get the primary winding inductance value that would be needed for this flyback transformer to operate in the continuous conduction mode. We know the number of primary turns is 1 here. We have taken 1 here. This supply voltage at the maximum. The supply voltage was 36 volt. The load voltage was 5 volt. The input ripple I have just mentioned that we are going to set it at 60%, so it's a 0.6. The switching frequency we have also selected. We are going to operate at 250 kilohertz. The output power I have mentioned in the beginning is 20.2 watts or watts. And this the number of secondary we have calculated. Whatever secondary voltage, the supply is again going to be maximum. This again the number of primary turns, and again the what is the output power. Okay, so we will, once you put it, you are going to find you are going to get the value, and that value would be your number of, it would be primary winding inductance value. So now we want to calculate the primary winding ripple current, and we also want to have a primary winding. One we need a ripple current, one we need a ripple current, I ripple. The other we need a peak current. So to calculate it, we can use for the ripple current delta IL M is equal to V supply dot D by LM dot switching frequency. So we know it supplies 18 volts. The D is basically, we have calculated it in the previous. We have taken the LM, we know, we have just calculated the LM. Switching frequency we already know. Similarly, we need to calculate the primary winding peak current, and the primary winding peak current is given by the formula P out by V supply D plus delta IL M, which is basically the primary winding ripple current, by 2. Putting the values again, you are going to get the primary current primary winding peak current. So now we need to select a current resistor value. I have mentioned that here the current resistor value we are going to use. Now what is the current resistor? Where basically we are, just a second. Yeah. So I have a flyback transformer here. Here we have a MOSFET here, and in the MOSFET the gate will be driven by the gate pin. There is a CS pin here, and this is the peak GND pin of the IC. In between, then we are going to connect a resistor. So we have the resistor that is named as RS. Okay, so this resistor is basically an RS. This is the work of this resistor is basically the current sensing. Okay, so we are basically sensing the network component, the current sensor. So this resistor is going to sense the switch current for the control loop, and it's going to set the peak current limit value. Okay, and we would be also needing a low pass filter. Let's see where it was, the low pass filter. Yeah, okay. So we will be requiring a low pass filter also, and the low pass is just an RC filter we are going to use, and it's going to reduce the impact of any high frequency noise on the current sensing signal. And we are going to set the external slope compensation. We can set an external slope compensation, which I am not using for the supply in this particular circuit, but I can use it. Okay. and that basically is not that why I am not using it, because some circuits do require an external slope compensation. That means I have just mentioned an RS here. Now I mentioned that I would need a low pass filter. That means we are going to have an RS here, and here we are going to basically draw here only. We are going to have a low pass RF here. We are going to have a RSL if the slope compensation, if an external slope compensation required. We have a capacitor here, and it forms a low pass filter. Okay, and this output is going to be in this pin. Okay, this output would be in the CS pin, not directly here, but we are connecting the CS pin through this LPF. Okay, so this resistor is basically selected also. We need to avoid triggering a peak current limit protection when the minimum supply voltage is present. So we have a V supply pin here, and we need to supply the maximum output power here. So if we to avoid triggering the peak current limit protection, okay, we need this pin, this resistor comes into play, or it helps us to avoid that scenario. So because of the component tolerances and the efficiencies of the regulator, this peak current limit is set some margin above the calculated peak current of the transformer winding. So we generally use a margin of 20% to 30%. Okay, and again we have the formula for that, and putting the value we can select the peak limit set. Okay, so we are basically first doing calculating the maximum current sense resistor value, assuming that this we are not using the external slope compensation. So this is 0 ohms here, and then we can calculate this, what would be the maximum value of the this current sense resistor. So if the calculated value, now I suppose if we are choosing a calculated resistance value, we can calculate the maximum value, we can calculate the other value also. So if the capacity, let's say the other value that I am choosing in RS underscore SL, if this value is less than this maximum which we have just calculated, then we are going to use this selected value, and if suppose this value comes out to be greater than this value, then what value we should choose it? Basically we can then choose, we can decrease the current sense resistor value, or we can add this resistance value here. So if we are decreasing the current sense resistor value, it is going to increase the effectiveness of the internal slope compensation, and with no external slope compensation the peak inductor current limit will be constant regardless of the duty cycle. And the low current sense resistor value, it results in a large switch peak current limit value, which increases the required saturation current of the primary winding. And we are adding a external slope compensation. So the peak inductor current limit is going to vary with the supply voltage when the external slope compensation is added to the current sense network. Okay, now I mentioned here RF and CF. So how we are going to, what value should be used in the RF here, because this low pass filter is going to help mitigate the impact of the leading edge spike on the current sense signal here, and this is basically selected between the 10 ohms to 200 ohms, and depending on that we can even select it the capacitor value, like we can say okay, the capacitor value of the low pass filter would be less than equal to 150 by 3 times the RF, so this RF as the switching frequency. Simple. So that is basically just a formula that's given. You have to put the value there. Now we need to have to select the MOSFET value also. The MOSFET is basically going to be the MOSFET. We know this is the flyback controller. Going to, for this flyback controller, we need to note that this MOSFET is going to have a conduction loss and a switching loss. The conduction loss, they are going to be dominated by the RDSO and resistance of the MOSFET, and the switching losses that occur during the rise time and the fall time of the switch node. So when the N channel MOSFET is turning on and off, okay. So during the rise time and the fall time, the current in the MOSFET channel and a large voltage drop across the drain source are present. So the longer the rise and the fall time of the switch node, the higher the switching losses. Okay. So we have to select the MOSFET such that we are going to have a minimal of the parasitic capacitances, and that's going to result in the decreasing the switching loss, and the total gate charge that must be small enough to keep the internal VCC regulator from entering the current limit, because we are using a VCC here, this IC that I have earlier drawn it. Okay, so the total gate charge, again we can use the datasheet of the MOSFET, and everybody knows how to, any graduate knows it, any diploma holder knows it, how to see the total gate charge from the datasheet. You have to use the component datasheet only or the manufacturer, and you can calculate the total gate charge, and then RMS current of the MOSFET can be easily estimated. The RMS value would be definitely the square of the two terms here, and by estimating it, we can select a small MOSFET with a small RDSN. So the RDSN value once calculated, we can also the drain to source breakdown voltage rating of the MOSFET, we have to select it, and that's need to be selected here, because here we have to note that flyback transformer is basically the flyback action is happening. Okay, that theory was explained in my last video. The flyback action was not only the flyback action, the other thing that I mentioned, the reflected secondary output voltage. So that's going to be higher than this reflected secondary output voltage plus the maximum input voltage. Again, simple addition. And here, due to the parasitic leakage inductance of the primary winding, okay, the switching node voltage is going to ring well above the value, whatever value we are going to calculate it. And to avoid this ringing on the switch node, or the voltage clamp can be added. Okay, now we need to select a diode. Again, the diode, what should be the rating of the diode? So the diode, it should have must have a reverse voltage that's greater than the reflected voltage for the primary transformer winding to the secondary winding. Obviously we have to also include the secondary load output voltage, that's very basic, and the reverse voltage of the secondary diode can simply be calculated. Number of secondary turns we know, number of primary turns we know what is the V supply, we know what is the V load, just add it, calculate it, we are going to get some value. And due to the leakage inductance, there is a voltage, there is a negative spike when the primary side switch is being turned off. So we are going to use a snubber here. Snubber, even if we are going to add a snubber, some voltage margin should be added to the voltage, and simple is completed here. And we need this output capacitor value is also one of the key components of the design. So this output capacitor is required to smooth the load voltage ripple, and it provides an energy source during the load transients and provides energy to the load during the on time of the MOSFET, as explained in the flyback video. Okay, so basically we can use it's basically related to the control loop crossover frequency. And for this estimate, we are basically expecting that the control loop across the control loop crossover frequency is going to set by the 1/5 of the RHP. That's a right up plane of the zero frequency. and we need an input capacitor. If you have seen, initially I have put here an input capacitor here. So this input capacitor is going to smooth the supply ripple voltage during the operation, and for the design we are taking the input voltage ripple to be less than 50 millivolts. Okay, and when the supply voltage is set at the minimum value, and we are again going to just put the values and going to get some value here. Now in an IC, if you remember, I have mentioned an under voltage LO pin, UV under voltage lockout pin here, and again we need a resistor with that pin, because we had a voltage divider here. I am again drawing the voltage divider here. So this voltage is going to this under voltage UVLO, and this to the analog ground, and this would be ground. So we have a resistor divider. This is the input supply here, and is going to set the minimum minimum operating supply voltage of the regulator. And again, after setting, what would be the minimum voltage here? Just a simple formula we know, because it's a voltage divider, it will be V1 minus the 2 voltage we are going to select it divided by current. That formula we are going to use and going to select both the values of this voltage divider resistors. So now we come to the control loop compensation. In the control loop compensation, if you see, I had basically drawn a optocoupler here. This was the comp pin, and the comp pin, if you see, it is going into the comp pin. Here I have drawn a capacitor, here I have drawn a resistor ground, and this will be here. Okay, so let us now see what basically the control loop compensation is here, and it is basically going to stabilize the control loop for the peak current mode control, because it is going to be peak current mode controlled regulator in the CCM operation. So the feedback path, this circuit rather, the circuit, and here also, if you see, here also we have a Schottky diode here, and a capacitor here, resistor here. Okay, and this is the grounded. Here we have one resistor, would also didn't draw here. There would be one resistor that we need to put here, one resistor here. The load supply would be connected to that. Okay, and this I have drawn it, and yeah, so the circuit is complete. This is one resistor here also. So let me explain these two things. So this optocoupler is going to maintain the voltage isolation between the primary side and the secondary side. And here I haven't used the FB pin. I have mentioned what was the role of FB pin there. It was an inverting input of the error amplifier, and if we want, we can connect a voltage divider to the FB pin to set the output voltage. Okay, or we can even connect the low side feedback resistor close to the analog pin, but I won't be using any of these things. I am just putting it to be the ground, and I have drawn here no, this I haven't drawn it basically. So we know this is a compensating capacitor, and this optocoupler is going to have its own parasitic capacitance, and that value is going to depend on this value. So the value of this parasitic capacitance of this optocoupler depends on this pull-up resistor here, and okay, and suppose now if we assume that this compensating capacitor is greater than this value of the parasitic capacitance. Okay, we are basically, if we are going to, we should take basically the compensating capacitor greater than the this parasitic capacitance. So a pole is going to form by this this R, this resistance along with the parasitic resistance. It is going to form one pole here, and now we need to place the zero end poles on the feedback path to achieve the stable operation. And the loop compensation selection is basically, we need to supply the feedback resistor selection. We need to select the first feedback selection. Okay. So this is the feedback resistor selection. Here we are going to first select this value. So we know what is the voltage reference. We have to select the voltage reference. So we are using the voltage reference, the popular, which was given a decades ago, TLV 431, because it's going to have a voltage reference of 1.24 volts here. For higher volts, we can choose the voltage reference of 2.5 volts, 2.5 volts or 1.24 volts. As we need the output voltage of 5 volts, we are going to select the design voltage reference of 1.24, and it is going to allow the more headroom. Okay, and there are two resistors here also. So this lower feedback we can calculate it. Now we have chosen some value for this feedback resistor, and we know what is the voltage divider rule. We can basically again then calculate the value. This value is also going to, we need to select this value also, and it depends, this value depends on the auxiliary winding of the winding voltage, or rather if the flyback transformer do not have an auxiliary winding, I can use the VCC output pin voltage of this regulator of the IC which I have just mentioned, just used it. So now we have to come to an optocoupler, and when we are selecting an optocoupler, we know we need to know what is basically the current transfer ratio. What is the current transfer ratio? What is the diode voltage drop on the secondary side, and the capacitance, because this is a BJT, what is the capacitance of this BJT on the primary side? Okay, so the current transfer ratio can be large as 600% variance. And we basically use the CTR value between 100% to 200%, and the diode voltage drop, it impact the selection of this R LED. This resistor value is here because it's an LED here, and this diode voltage drop needs to be small enough to allow the voltage reference to be supplied with an adequate voltage to ensure the operation. So I have chosen the voltage drop of the diode as 1.4 volts. Okay, as I have earlier mentioned that this pull-up resistor and the parasitic capacitor is going to form a pole. So our crossover frequency of this loop is going to be limited. Okay, and now we need to select this compensative resistor value. and because it's going to directly affect our crossover frequency of the control loop, and the higher the crossover frequency, the faster the control loop is going to react to the transient of conditions. And if we going to use a lower resistor value here, it's going to lower the crossover frequency, but it's going to make our control loop stable. Okay, so last thing which is left is this capacitor value. Again, this we have a capacitor here, resistor here. It's going to set the low frequency 0 of the compensation network. Okay, now this completes our circuit only. The one thing I would like to go on the what basically the functional block diagram of the functional block diagram. If I am to go the functional block diagram, I want to just draw one functional block diagram of an IC. That is that the circuit is basically because I have covered up all the components, how to select them. I have only excluded the manual calculations, or if someone has a calculator, you can just put a calculator, or you can design a calculator. Now let's go what is basically an IC which we have used here. Let's go on its functional block diagram. Okay, let's go on the functional block diagram. So the functional block diagram of that IC, of this, we have a current supply here. Let me just go fastly. Okay, I draw it by stage only. It would be more better. So we are going to have a. Now first thing that I mentioned that our this IC was giving us our line under voltage lockout. So line under voltage lockout, it was basically achieved from this thing only. We have a current source here, I, U, V, L, O. We have a stereo Schmitt trigger here. One more, we have an OPM Schmitt trigger here. So what we have seen, we have connected it to the voltage divider, if you remember, and this was the grounded to an AGND pin. So during the power on, if the bias pin voltage is greater than 2.7 volts and the under voltage lockout pin voltage is between the two threshold pins, one would be this, I have drawn somewhere wrong here. This would be actually between here and this between here. Yeah, sorry, this I did a mistake here. So this pin and this pin voltage between these two threshold voltages the under voltage lockout pin is between these two voltages. Okay, if the time duration is greater than 1.5 microseconds and if the bias voltage is greater than 2.7 volts, the device starts up and the internal configuration starts. This is the startup of this IC. Okay, so we are having an internal startup delay here before it's going to enter into the standby mode, and in the standby mode the other pins, the VCC regulator and an RT pin, they are going to be operated. We know the soft start was grounded and there is no switching at the switching pin. And when this under voltage lockout pin is greater than the threshold voltage, it enters into this mode. One mode would be we are going to get here, another mode is going to be get here. Okay, I am closing this.